Morty, we've got to turn the project in early.
Hey everyone, how are we doing? Good to see you here. William and Cameron, Chapter 15 homework with some hacks. I know we never got to the hacks. Shall we do some Chapter 15 homework with some hacks? That sounds good to me. Samantha, good to see you here. Let's do some Chapter 15 homework with some hacks. I like that idea. Hacks stands for hypothesis, annotate notation, check conditions, solve for p-value. We're going to do some of that right here. Hypothesis, annotate notation, check conditions, solve for p-value. Say it with me again, Cameron in the chat if you want, as I wake up Mubot right here. Hypothesis, annotate notation, check conditions, solve for p-value is hacks. Good job remembering hacks. It was like right at the end of class, I was like, oh darn it, we don't got enough time to do the hacks. But we did, what did we do? We finished off with, we talked about degrees of freedom, we talked about all that good stuff. We did pretty much most of everything we needed to do. And we covered a lot more. Hypothesis, annotate notations, check conditions, solve for p-values. And we got some upcoming assignments here. My gosh, I'm gonna move the microphone a little bit. Gotta make it so I can hear the soundboard. I don't use it nearly enough these days. There we go. That better? That better? One more time. One more time. And then we'll do, which one do you want to do from Chapter 15? You want to do the whole Chapter 15 homework? We can do the whole Chapter 15 homework. Let's do Chapter 15 homework complete. The homework, I don't have to do different versions of. Homework's just one version. Okay, Chapter 15 homework. Preview it. We gotta text my wife. Okay. I know I'm hoping, I'm guessing 75. Had our chimney inspected and they're saying $2,000 to fix something. Oh my gosh, everything's expensive. Everything's expensive, everything. Okay, let's put in the notes. Okay. Okay. These music. First string. 353, and we have here Chapter 15. For Stats 201, Chapter 15. You ready, Cameron? Chapter 15 homework. Let's do it. Here we go. Wrong button. Let's look at my phone. Okay, we got some Chapter 15 homework. So there's a lot of things we were memorizing from the last class, and the null has the what? Any time you see the null hypothesis, I think it's saying choose the correct null hypothesis. I'll talk about what a null hypothesis is here in a moment. The null has the equal sign. So it actually makes this question super duper 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 easy. To get water leaks. So that's not good. So with this right here, the null has the equal sign. And great job, Samantha and Jennifer. You hear the Zelda ringtone in the back. That's when my wife is texting, so I'm like, I gotta look at that text. Oh, there you go. Hey, look at. Cool. Well, we're dealing with leaks. Let's go 10,000 points. So with this right here, the null has the equal sign, but let's try writing a null hypothesis out for ourselves. You ready? So we're basically going to do this question, but a different version of it to see if we can get it. Imagine I ask you, Brian believes that more than 60% of students love Taco Bell. So now to write out a null hypothesis, you need to do the following. So to write out the null hypothesis, we need to have here a population parameter and then equals hypothesized value. So if we said Brian believes that more than 60% of students love Taco Bell, what is the null and alternative? So can you write out the null and the alternative with just this information? The answer is you can. So boom, Jennifer's already got it right there. And notice Jennifer's using the perfect notation. Great job, Jennifer, right there. The null has the equal sign, and what you want to do is you'll choose between the population parameters of either p, mu, or mu1 minus mu2. Now, the way you know which one to pick is based on the question, where we're talking about the proportion of students who love Taco Bell. Mu would be for mean, like if we're testing the true mean, and mu1 minus mu2 is when we're testing the true difference between the means. The hypothesized value, as Jennifer noticed right here, is 60%, which is what we are hypothesizing is true. So the null would be the true proportion of students who love Taco Bell is 60%. And here's the thing you want to do, is you want to be able to read this and write this. You want to be able to go here and say the null states, that says the null states that the true proportion of students who love Taco Bell is equal to 60%. Does that make sense? The null has the equal sign, and all you have to do to get the alternative is choose between one of the three signs, the less than, the greater than, or the does not equal. And the question or the researcher indicates the sign of the alternative. How are people doing with these ideas right here? If you know how to write the null in statistical notation, that's a really good thing to be able to do. Knowing that p is the true proportion, mu is the true mean, mu1 minus mu2 is the difference between the true means, or the true difference between two means. And then the hypothesized value there is based on the question. And this value, ooh, I'll throw 10,000 points if anyone knows what this value is in notation. What's interesting is it's not p anymore. What is that value in notation? Great job, Cameron, right there. What is that value 0.60 in notation? Boom, already knew it is p naught. That is p naught, which stands for the hypothesized true proportion. So if you use p, you'll use p naught over here. And if you use mu, you'll use mu naught. And the other one is usually 0 for the difference between the two means. It's actually delta naught, I believe, for differences. But that's what we have going on right there. There are the nulls and alternatives. We check it, we got it right. I think the next one does the same thing. It just asks you what the null is, and we're hypothesizing that you're going to get a random card. So you would get a random card that is that suit 1/4 the time. The null states the true proportion of cards in the deck that you get is 1/4 of that suit. The easy thing, there's so many ways to do it, and I really like the next parts of this right here. Peanut. Oh my gosh, we should put that in there when people say P naught. Here, give me a moment, camera, we'll do it here next. But the next question is really where it tests your knowledge. So if you want to know if you know how to do these, this question 3 right here, we'll put question 1 and 2 on here. Question 3 is where you really test your knowledge on if you can do this. So here we go, we're going to mark this in the chat, chapter 15 homework, question 3, and let's look at this. Now, whenever you write the null and the alternative, the first thing you want to do is talk to your friend. He's not here today, but what is our friend? He's our creature for the class, because it really boils down to knowing what or what. If you're part of the Stats 1 lore, you know a cat named what? You want to say cat or quant? I wish I could just have him appear right there and say, I got to load him up. Cat or quant? Cat or quant? You have to have cat or quant. So cat or quantitative. You have to have cat or quant. So with this right here, we are asking, a slot machine says it wins or gives you a win 7 out of 100 times. I'm going to let you pause and think about it. Is this cat or quant? A slot machine wins 7 out of 100 times. The cat or quant? Cameron already did it. Cameron is right. I lied. Samantha's just trying to see if people will understand. Samantha, 10,000 points right there. No points for Cameron, though. I'm just kidding, Cameron. But a perfect answer right there. It's win or lose. In notation, what is 7 and what is 100? So does anyone know what 7 is in pulling fast one right there? Like, I'm going to trick Cameron on this one. So does anyone know what 7 is in notation, what 100 is? So you win 7, like they claim you win 7 out of 100 times. It is actually successes and well, the failures would be 93. N is the sample. It's kind of the claimed success rate. It would actually solve for P naught. So 7 over 100 is P naught because 7% is the claimed or the believed or hypothesized success rate. So it's kind of an X over N, but it's not like we did 100 samples. It's saying this is the expected success rate. 7 over 100 will get you P naught. So P naught is the value right there. Look, it's over there at the hypothesized value. The null has the equal sign, the alternative, and they're asking, does it really pay out this amount? So think about this. The alternative, would it be greater than, less than, or not equal to? The question is, does it really pay out this amount? So what would the alternative be? The alternative is based on the way they worded the question, and they didn't really give a direction. So they're asking, does it really pay out? Yep, not equal to. And from here, we just say P because that's proportion. We'll never use X bar. We'll never use P hat in these. Well, like they use them in the equations, but not in writing the null and alternative. And then that's proportion. And then there's P, and there's P, and good work. Good practice on that. Next one says, last year's customers spent on average, going right there, this much on the website. The company wants to know if it has increased. So what are we going to pick for the population parameter we're testing? Last year's customers spent on average. So what's going to be the parameter we're testing? The parameter we're testing is what? Because customers spent this on average. Mu? Yep, it's going to be mu. And you can just put mu in for all of these. And then the null has the equal sign. The hypothesized value is this. They're asking if it increased. So we just put what here now? They want to know if it has increased. So that's where you go to the alternative, and they're asking, has it increased? You always look at the researcher's question to see which direction they're going with it. Has it? Yep, greater than. Just that simple. We won't use greater than equal to, less than equal to. We'll just use not equal to, less than, greater than. And since we're seeing if it's increased, we're good on that. A pharmaceutical company wonders if the new drug has a cure rate lower than this. So cured or not cured, and 30%, are we doing cat or quant? So here's things. We're doing cured or not cured of 30%. Or we're seeing if it's lower than 30%. Well, no, because P naught and mu naught are these values over here. We're doing cat for this. This is P, so we are testing P. The value on the other side right here, this is mu naught. 0.30 is mu naught. So you could write P equals P naught. So you could write P equals P naught, but P is the first thing because the true proportion is equal to the hypothesized proportion. Does that make sense? Good questions, Cameron, right there. So the last value is the naught value, just to see the notes we took. And great job. It takes a lot of practice to do this. Oh, there he is. The P naught or mu naught would be the last value. And 0 is the hypothesized difference between two means, like P naught, mu naught, mu1 minus mu2, hypothesized difference of 0 most instances. And so we're seeing here if it's less than, lower. Last one, might be the last one, I think. A bank wants to know if the percentage of customers using their website has increased. So from 40%. So is this P or mu? P or mu? So the way to do it is to ask yourself the question like Cameron did earlier about what they're doing. Bank wants to know if the percent of customers who use their website has increased from 40%. So is this P or mu? How would you collect data on this? I think it's very easy to make mistakes on these. P, because it's it's P, because it's category, it's do you use the website? A lot of times people think it's and don't worry if you get it wrong, because categorical, because do you use the website? People see 40% and they're like, oh, wait a minute, 40% is numbers, but be careful because it could be quant. But the question is, do you use the website? And so phrase it like the mean of people who use the website or the proportion of people who use the website. And even says down here, the proportion of customers using the bank website makes more sense, makes it P. Great job, everyone practicing right here. If you're here, you can see that it takes some practice, and always ask yourself the question like, what am I trying to say? The mean of people who use the website or the proportion of people who use the website? And that's where you get the practice and you understand the difference between P, mu, and mu naught, mu1 minus mu2. P equals 40%. They want to know if it has increased, so that's the alternative. Are these easier now? What do people think? Like once you do them a bunch of times, it gets easier. What's the null hypothesis? There you go, has the equal sign. What is the appropriate alternative? So let me ask you this right here. When we are doing the alternative, we always look to the what? Here's a huge note you want to have. Do you look to the data or do you look to the researcher's question? When you are doing the alternative, do you look at the data or the researcher's question? question, the researcher's question. So the researchers are wondering, suppose I test whether students' textbooks costs for this semester are higher. So that's literally the, right there, that word, the higher, is the sign of the alternative, and it's not X bar because it's the sample mean. We're not testing the sample mean. I mean, we are testing it as a estimate of the truth, but we're not trying to make inferences about the sample mean. We're trying to make inferences about the true mean to see if there's evidence that the true price of books is higher on average. So man, we are flying along. How are you feeling, Cameron? Is a longer quiz, 11 questions, but we're already half-ish way through it. Just a few minutes into office hours, so we're doing really well. If you're here, you're just getting this homework done. Homework, no more. So let's put another timestamp. Statute 1, chapter 15, homework question 6. Here we go. A test preparation company claims that more than 50% of students who take their... Why do I really accentuate that? More than 50%. That's the claim. The claim is the one that requires evidence. And my gosh, I am popular today. The claim is the one that requires evidence. And so why do I accentuate the more? It tells us the sign of the alternative. Exactly. Great job, Cam, right there. The sign of the alternative. Perfect answer. Ringtone jump scare. I know. Well, my wife's texting a lot, so I want to make sure I see anything important. More than 50%. So that is the sign of the alternative. They will improve by at least 10 points. So did you improve by at least 10 points? Is that proportions or quantitative? Did you improve by more than 10 points, and they say more than 50% of students will have that? Is that cat or quant? What do you think? Cat or quant? We're trying to see if more than 50% of students will improve. Yep. Because did you improve by at least 10 points right there? That's definitely going to be cat. So is the alternative one-sided or two-sided? So a two-sided alternative is the does not equals alternative. A one-sided alternative is simply the greater than or less than. So since we're testing more, is this a one-sided where we plot to the right or to the left? Or is it a two-sided where we do the does not equals? So one-sided means greater than, or it could be less than. Two-sided alternative is the does not equals alternative. This is a one-sided alternative. If you're wondering why it's called one-sided, let me go over here to the applets. When you plot a one-sided alternative, if you do a greater than, you graph to the right of it. If you do a less than, you graph to the left of it. If you do a two-sided, you graph both sides of it. So a two-sided alternative would be the outside of the curve shaded. So usually we go here and we go find p-value using this. And there's a two-sided alternative. There's the less than alternative, and there's the greater than. So hence one-sided on these, one side of the curve is shaded when you go above or below. And then outside is going to be the does not equals. The button you click would be dependent on, did you click the greater than, or did you choose greater than, less than, or outside right here. I want to show you something. When you do the greater than, look at this way right here. The greater than alternative shades to the what side of the curve? Just look at the way this looks. The greater than alternative shades to the what side of the curve? Look at that right there. You go to your point, and you literally shade in the direction of the arrow. Does that make sense? The right side. So if you want to know which way to shade, look at the sign of your alternative, and then it shows you which way to shade past your test statistic that you find. More on that coming up as we get to some of these questions, but understanding that the sign of the alternative determines which way you shade the curve. So it's one-sided right here because we're trying to see if there's higher scores. Very good answer right there. The p-value is this. So what is a p-value? P-value is the probability of our results or results from our stream having by random chance variation given that the null is true. So that really doesn't make sense when you say it that way, but let's talk about one of my favorite examples right here, Brian running around a track. So if I were to run around this track and I were to tell you that I can run my miles in 6 minutes, your null hypothesis would be, a better Brian over there, you would say Brian claims his average mile time is 6 minutes. Let's say we get a p-value here of 0.98. Well, what's interesting is with a p-value of 0.98, I might not have ran exactly 6-minute miles. Technically, we need an alternative, so we'll do he's not a 6-minute mile runner. Or his mile time's greater than, we'll do it like the other one. So mile time is greater than 6 minutes. So with this right here, you know what? Gas station's going to watch this and figure out the small thing. We'll go with this. There we go. I might have had this right here. What does this mean? Brian's what was what? What does that thing up there in the top right mean? Good to see you there, Caroline. What does that thing in the top right here mean? What does that thing in the top right there mean? What does that mean? Brian's what was what? So this says, the top left says, my null hypothesis is Brian's average mile time. Y hat is the sample, or Y bar technically. Y hat is predicted. Great job, Caroline, right there. Y bar, that's Y bar right there. So Y bar is the sample mean of variable Y. And so Brian's average mile time was 6:01, very close to 6 minutes. So you would ask, if Brian is a 6-minute mile runner, because let's write down what the p-value is. The p-value is the probability of our results, or results more extreme, occurring by random chance variation given the null is true. Okay. So the p-value is a probability of likelihood of what you observe given the null is true. So think about this. Is 47% likely or unlikely? Don't even worry about everything else yet. If I tell you 47% chance of rain today, are you going to grab an umbrella? 47% chance of rain, you got a big interview. Are you going to go grab an umbrella? There's a 47% chance of rain, you got a big interview. It's major important. You're going to grab an umbrella. You say, there's a good chance it's going to rain today. And you're like, someone's like, but it's less than 50%. You're like, but still, it's a high likelihood for like rain. I mean, like 47%, it could definitely rain. It's quite possible it's going to rain. So think about this. The p-value is the probability of our results. Our results are this. A result more extreme would be a time greater than that. So a result more extreme, it keeps highlighting that every time I do that. So the p-value of occurring by random chance variation given the null is true. So let's input these phrases into here. You ready? There's about a 47% probability that Brian would run a mile time of 6.01 or slower, given, due to random variation in his mile times, given he is a 6-minute mile runner. Does everyone see? I'm just taking the colored things and putting them in. There is about a 47% probability of Brian running his mile times in 6.01, because that's the result, or a time more extreme than that due to random chance, given he is actually a 6-minute mile runner. So does it sound like what I did was likely given I'm a 6-minute mile runner? Yes or no? Does it sound like my result right here? And think of what I said with the rain. Does it sound like my mile time is a likely time to see given I am a 6-minute mile runner? Does it sound likely or unlikely? Yes or no? Think of the rain example from before. It sounds likely, right? You're like, yeah, that's quite probable. Like what he did here is likely given he's a 6-minute mile runner. Does that make sense? But then you reverse it. And now you go over here and you put in a p-value. This thing is possessed. I'll tell you what. Now we go here, and if that's the probability of rain, you're going to say it's unlikely it's going to rain. And then we put in a new mile time of 12 minutes. Right here, we'll go 12 minutes. And so now this is the probability, which is virtually impossible. And Brian's result is 12 minutes. Now think about what this would lead you to do. If Brian says he can run his miles in 6 minutes and it takes him 12 minutes, I'm like, it's still possible that I'm a 6-minute mile runner. You're like, yeah, but I don't see it happening. Like, it could rain any day, but I don't see it happening today. It's super unlikely. Well, Ariana, good to see you here. What would you end up doing with the null hypothesis here? Think about what you would do with the null. So in this instance, you would what the null right here, because you're like, I saw you run a mile in 12 minutes, which is very unlikely given you're a 6-minute mile runner. I reject the null right here. I reject the null. I have evidence that it takes you more than 6 minutes. In the previous one, we would fail to reject the null and we would not have evidence for the alternative. So that's kind of key right there. I really like that example. Hopefully it makes sense because these questions are just on other data, things that doesn't make sense. So if a p-value here is high, then there is not evidence for the alternative. Low p-values are we reject the null with and we have evidence for the alternative. Like this would be when Brian ran his miles close to 6 minutes. There wouldn't be evidence to conclude Brian runs his time greater than 6-minute miles. And thus we would think that is approximately, I think, right? We're not going to reject the null. Wait a minute. Evidence includes, oh, they're talking about the alternative only. They're trying to find more. Yeah. The p-value of this, there is not sufficient evidence for improvements for more than. Sorry, they're talking about the alternative right there. I misread it. The p-value of this, then there is sufficient evidence to conclude that the course improves scores for more than, still more than. It's a good question-ish, the way it words it. I'd prefer you know how to write our phrases right here, like with a p-value of blank, I reject the null. And let me go find this really quick. I'm gonna take a screenshot of it because that's probably one of the most important things if you are studying, and thank you to everyone who uses these office hours and other times to learn the material, because it's one thing to ace the assignments, it's another thing to, where is it? Hours. One thing to ace the assignments and another thing to understand the material and do really well on it. So I'm going to go grab our video from class. Shorts. I need to make some shorts, right? So class 29. Why not? Oh, we only have like 5 more classes. I can't believe it. So, okay. I'm going to take a screenshot here of this video. Probably could have written it down about that time. Here we go. All right, here we go. In 2 seconds, I'm going to screenshot this and bring it over here to this screen. Okay, and there we go. I'll bring it over here. And there we go. Okay. So here's what you need. The dates of the classes are behind. I think it stays the 15th. Oh, on YouTube? Really? Oh, no. Oh no, oh, did I write the 15th on this? Oh, I gotta fix that then. So there is that right there. No, this is the right date, I think. So there we go, right here. With a p-value of your p-value, I reject or do not reject that the null, state your null hypothesis. This is evidence or is not evidence for my alternative that. Off topic, question about the project doesn't matter, the order we put the info in, or is there any way? I'll do it in order of the project. Good question, Samantha, right there. It should start with the executive summary. So you'll do executive summary, proportions, I think, do in order the project, and then start with your, finish with your outro. Good question, Samantha, right there. Good morning, Sarah, right there. So please write this down if you haven't. Take a screenshot of it. Know how to use it, because we will use this in class today, and you will write this out for the test. This usually is where a lot of people lose points, because they have no idea how to state their null and alternative when they finish up a problem. Oh. In a criminal jury, one option is to declare the defendant not guilty. Great job, William, right there. In hypothesis test, this is equivalent to which of the following? Failing to reject the null. We do not accept the null as true. Really good question right here, because you just don't accept the null. It's not the way we do it. I guess I'll mark that really quick. Mark that question. We're almost done with this. 28, 23, step 201, chapter 15, homework, question 7. So great job, Samantha, right there. So many points. Next question says, the probability of seeing sample data like those seen or something even less likely given the null, or more extreme, it should say more extreme, given that the null is true, is the what? The probability of seeing something like your result, the probability of seeing something in your sample, or seeing something more extreme than it, something less likely if it's a less than alternative, is a what? See, they went for a less than, that's so funny they did a less than alternative. It's more extreme, it's a p-value. Yep. That's the p-value right there, and the z-score is the standardized result. The null hypothesis is the starting belief, and the alternative hypothesis is the one that needs evidence based on the data. Which of the following is the correct interpretation of a p-value that's not very small? What is a not very small p-value? Any p-value that's not very small is greater than what value? So a not small p-value is a p-value greater than what? Finish that sentence. A not small p-value. 0.05. 0.05 is the decision point. If something is less than 0.05, good job there, William and Cameron and Samantha. If something is greater than 0.05, or equal to or greater than 0.05, we fail to reject the null, and we would say that what we saw is what? So we could fail to reject the null and say our results were what by what? Great job, Caroline, also. Don't worry about what's on the screen right here. If it is a large p-value, it's likely, by what? What we're seeing is likely by what? So you can go back to the p-value interpretation, likely by random chance given the null is true. Likely by random chance given the null is true. Mewbot just loves that randomness right there. You like likely by random chance. Like when we talk about Brian running his miles in 6:01, that's likely by random chance if he is a 6-minute mile runner. Does that make sense? Think about this. Are you going to see me run my miles in 6 minutes every time? Like, who's your favorite? Does anyone have a favorite basketball player? Does anyone have a favorite basketball player? Who's your favorite basketball player? If so, tell me who your favorite basketball player is. Batman? Or, yeah, damn. Michael Jordan. So let's say Michael Jordan is claims he could still make 80% of free throws. Michael Jordan's like, I can still make 80% of free throws. Dolly Parton, she's great at everything. So Michael Jordan's like, I can still make 80% of free throws, and you watch him go out there, and he makes 77% of his free throws. And he does like 18 free throws. I think he could do that with 18 free throws, or 27 or so. Yeah, keep up at night. So Josh Peck right there from Drake and Josh, he just came to campus, didn't he? I wish he had gone to that. So if I'm the basketball player. So if Michael Jordan made 77% of his free throws and he claimed to make 80%, just going off of that, we could do the stats on this, but do you think that Michael Jordan's a liar? Or would you say he made 77%? That's basically 80%. You see where I'm going with? That would be a likely result given the null is true because there's variation. He's not always going to shoot 80% every time. If he shoots one free throw and he makes it, he's a 100% free throw shooter in that moment after he's just done one. But he would kind of in the long run go towards 80%. But you would say, okay, he's close enough to 80%. I would believe him. It's actually close enough. So that's what we're saying when the p-value is high, that what we saw was likely given the null is true. So if we ran the results and we got a high p-value for 77% with Michael Jordan making that, claiming 80%, we're saying 77% is a likely result given he is an 80% free throw shooter. So what would we do? Would we believe him or reject it? With a high p-value, Michael Jordan made 77% of his free throws and he claimed 80% and the p-value is high. Would we believe his claim or reject his claim? The p-value is high. Would we believe it? We would fail to reject it. Exactly. And fail to reject means continue to believe. It doesn't mean accept. It doesn't mean accept. It means continue to believe because we don't reject it. And so I like to say don't reject, but yeah. So if we have a high p-value, what we saw in the data is not surprising. We fail to reject the null because we saw something likely given the null is true. Yeah, long explanation. Now here we go. Here's the real deal, putting together all of our knowledge. So was that question 9? I didn't mark it. 8, 9. Okay. Here we are with a much tougher question. Now, we have the Census Bureau claims that 18.1% of people in the United States are Hispanic or Latino. So they take a random sample of 423 people, and 49 of them are Hispanic. So now, with this, we need to mark our notations. Take a moment right here as I play a little music. Start telling me that notation.
Notation, brother.
What is the notation? Any notation. Any notation at all. You got it. Close. William, you're close. Remember, you always got to put P. So that's, you're close. Good answers, William. Let me throw you some points. We need some more notation on the screen, though. Any notation? I see some numbers on the screen. Got an N. Nice. What else we got? Close, Caroline. Make sure to remember the parameter of interest. What population parameter are we measuring? Everyone's got the sample size. Nice. Sample size 423. All right. What else? Anything else? I'll write the formula for you. Here's what you need. Great job, Jennifer actually has the, great job, Jennifer. Jennifer wrote the null. null states that the true proportion of Hispanic or Latino people is equal to, and they're trying to see if it is that, right? If it's different, which is different is going to be the sign of the alternative right here. So the alternative, so is it different? And so that's going to be right there. Yep, and I think someone else got another bit of a notation for us while we were talking right there. And so this is X. What is this? What is 0.181? Do you remember what goes over here in this spot? P equals what? So P equals what? P equals what value? What goes on the other side of it? There it is, the population parameter equals a hypothesized value. And in notation, that is what? Not mu. It's not mu, though. It's not mu. Not mu. On the other side, on the right side of this right here, it's going to be P equals what? So we chose P. And so since we chose P, like if you choose this, depending on what you choose, on the left side, not P hat. Not P hat. Think of anytime you see this naught right here, P naught. Saying earlier. So P naught right there. So this value right there is P naught. It really comes down to
notation, brother.
Notation. So I gotta, oops. So P naught equals this right here. There we go. That's usually the people get lost on that one. So if we have P naught, what else do you think we can find? Look at the equation down below and be like, oh, now we just need to find what? If we have P naught, what else can we find? If we have P naught, the complement, Q naught, right? Tell me if I made an error, that's Q naught. And then we can take and plug this into the equation, and we would get here P hat, which is, P hat is X over N equals 49. It's gonna be a little more than 10%, 4, 2, 3. So P hat right there, I called Mubot Poobot. Was that, no, he just talks sometimes. Mubot, he's talkative, he's a chatty bot. He's a chat bot, you know? I would never type for Mubot. That he would be offended by that. So, no, I'd never type for Mubot. 1158. There we go. See, look at it. He's just talking in the chat right there. So right here, minus over square root. What 23? Whee, my twos don't look good. Okay. All right. 423. Okay, so now we're going to find the z-score. The z-score is a standardized difference right here. The top part of the equation is a difference, and the z-score on the bottom, which we need to get first rather, because we're going to do the bottom part, 181 times 0.189 divided by 423, square root, don't forget to square root it. It's going to be a very large negative z-score of like negative almost 4, I think. What was I would guess in your head of what it should be close to? Negative 3.48. So that is the z-score, negative 3.48. There we go. So we've actually done most of this problem. We've pretty much done most of this problem. Let's look at the hacks right here. The first thing you would do when solving a problem is what? Think of hacks. If you don't know our hacks method in the class, we're going to talk about it right now. But what is the very first thing you would do if you were solving a problem on your own? You can do the hacks method, right? So what's the first thing of hacks? You can do notation. I like that right there. Notation, brother.
Notation, brother.
So you do some notation. Hacks. The hacks method stands for hypothesis, check conditions, annotate, notation, and solve for p-value. That's the hacks method right there. Don't cry, no. Don't cry for me, Argentina. Don't do that. Okay. So there's the hacks method right there, and you see at the very top of the screen the hypothesis we wrote out. So you have to practice writing your null and alternative hypothesis. To check conditions right here, with the first condition is easy. Who knows the first condition? Not Batman. But the first condition right there is random. We have to have randomly collected data, which it probably says. It was a random survey. Next condition is 10%. Less than 10% of the population is sampled. This is true because 423 is probably less than 10% of all people in the US or whatever we're trying to sample. It's not the 49 out of 423, it's the sample size. People sometimes get the 10% condition wrong, but you want to check it with n over capital N is less than 10%. That means the size of your sample is less than 10% of the population size. Population size isn't always listed, but this is of the United States. So I highly doubt you've sampled with 423 larger than 10% of the United States. So we've sampled less than 10%. And the last condition right here is the what condition. The last condition right here is the what condition, because this is categorical data. Or pause, because this is categorical data. The last condition is going to be what? Success failure, exactly. Success failure because it's categorical. Are you Latino or not Latino? Success failure. Don't worry about it. Good practice right here. Success failure because it is categorical data. So you have to understand the difference between categorical and quantitative. And we will do the nearly normal now for quantitative. And good work right there. Points for everyone in the chat. Practicing when we get to that third condition. Pause and say, is it categorical or is it quantitative? This time we're using P naught and Q naught because P naught is assumed to be P by the null. So we assume that P naught is the truth. So if we assume P is equal to P naught, well then let's use P naught as P right there. And we only have to check the smaller one, and it's going to be way more. The larger one's going to be larger. By virtue of the smaller one being greater than 10, they're both greater than 10. We could check the bigger one too if we want, and just multiply that by 423. So we pass all the conditions, and now we just have to solve for the p-value. Usually where people get stuck on these questions, we're seeing if it's less than, right? Different. Okay. What are we doing? We're doing a proportion, not a proportion t-test, one proportion z-test. We're using the z statistic, that's why, and it's for proportions. If you're wondering why I picked that name, the name is based on, we're doing a z, we found a z in the formula, and we're doing proportions, so a one proportion z-test. And they're doing success failure right here. Oh man, we actually have to do it? What? They want us to compute the success failures? What was the number I had on the screen a moment ago? How about everyone take a moment and find me the amount of successes here? They're actually having us find the amount of successes? What? Great, take a moment. Well, we need at least 10. So how many? You have to use P naught right there, and then you have to times it by the sample size. So take a moment. The standard deviation of P, no. It's more than, nope. It's random sample, this sounds right. How many successes were there? You have to take 423, yeah, so what would that be? Round them to the nearest numbers, I think. Round to one decimal. And so what you can actually do, you can take 423 minus 76.6, because that's going to be the other one. Or you can do it the real way and do, there we go, that should be right. There we go. So make sure to find both of those right there, know how to get them, and these two add up to the total sample size. If you got the numbers correct, NP naught and NQ naught will add up to the sample size. So that's how I was able to subtract and get them. You don't need to know every which way to solve it, you just need to know one. But then if you know another way to check your answers, you'll know you're good. If NP naught and NQ naught, doesn't really matter which is which. You can just call one of them your successes, one of them your failures. Thus, the conditions are met, and we would say we can use the normal. It is appropriate to use the normal techniques on it. So now here is where we get to our result. Now remember, our result, we just saw the z statistic was what? We just saw the z statistic was what? What was our z statistic? Negative 3.5. So which of these graphics looks like negative 3.5? Some of them don't even have the null at the center. The null is at the center of the graphic. Negative 3.48, right? So it's going to be right over here. There we go. Calculate the z. That's what we did previously, negative 3.48. Round to 2 decimals, check and answer. Find the p-value. Boop, 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 boop. There we go. How do we do that? Well, the p-value is going to be the area more extreme than our result. But here's the thing you have to be careful of. When you shade your p-value, you have to know if you're shading to the right, to the left, or both sides. How do we know if we're shading to the right, to the left, or to both sides? How do we know if we're shading to the right, or to the left, or both sides? The sign of the alternative. So since we're going to find a p-value using x, so we're shading to the outside because we did the does not equals alternative. Exactly. Great job, Cameron, right there. So because it's the does not equals alternative, we're shading both sides of it. And then we simply put in the negative 3.48 and the positive 3.48. And it's even probably smaller. There it is exactly. So it actually does round to 0.0001. But also think about this. Just visually speaking, you can't even really see it here. You can't even see the p-value. If I go a little more in, you can see it. So if you can now see the area below 3 just barely. There's the area below 3. But the p-value is the amount of area outside of it, and it doesn't even show on the other side. But think about it. How much area looks to be below this point? How much area looks to be below this point? About what? Like, just give me a number. About what % of area looks to be below this point right here? Basically what? Because I think you could have guessed it too. It's very like nothing, right? Now you would double it to the other side, so you could guess 0.0002 now because you would double it, but it's basically nothing, right? So this is virtually impossible. So the p-value is low, then there is evidence for the alternative that it's different, and also probably evidence less than. So since the p-value is low, reject the null, there's evidence for the alternative. Really good right there, and if we stated it with our writing, we would say with my p-value of 0.0001, let me read it off right here. I'm going to go back to the final page we wrote down right here. With my p-value of 0.001, I reject the null that the true proportion of Hispanic people is 18%. There is evidence for the alternative that the true proportion of Hispanic people is less than 18%. Does that make sense when I say it? Like, what I saw was very unlikely if there is 18% Hispanic people. I saw something that is evidence that there's less than 18% Hispanic people, and the p-value shows it because it's very unlikely. So let me repeat that again. With my p-value of 0.001, I reject the null that the true proportion of Hispanic people is equal to 18%, 18.1. This is evidence, since I rejected the null, this is evidence for my alternative that the true proportion of Hispanic people is less than 18%. If you need to state your null and state your alternative in those, state whether you have evidence, and you only have evidence when you reject the null. If you did not reject the null, you did not have evidence for the alternative. Try writing this out, try saying it out. With my p-value of 0.001, I reject the null that the true proportion of Hispanic people is equal to 18%. I have evidence for the alternative that the true proportion of Hispanic people is less than 18%. The more you can write it out, the more you can say it, the better you do on the test, and the more it makes sense. So the first thing we do in the HAX method is we write our null and alternative. We only got one more question. We'll finish off this homework here today. These are the tougher ones, but they're not that bad. About 15. So write out the appropriate hypothesis. So can anyone write this right here? They say the age at which men first marry is 23.3. So we're testing age of first marriage, and we believe it's 23.3. It's widely suspected that young people today are waiting longer to get married. So what would the null hypothesis be? What would the null hypothesis be? This is age at which you get married is believed to be 23.3. Mu, great job, Caroline, right there. Yep, because they're testing means, right? Is it getting easier to write these out? Mu 23.3, great job, Samantha. And then the alternative, it's widely suspected that people are waiting longer to get married, which is going to be a one-sided right alternative. So we're going to do mu greater than 23.3. Try writing it on your own, and then it's easy to see what the answers are. So boom, you get it down. You're like, what am I doing? Proportions or means? The null has the equal sign. And what value am I testing right there? Also, I want to state this, marking your notation, which will give us some more here in a second. What is 23.3 in notation? Since 23.3 is on the right side right here, 23.3 is what in notation? So think about what 23.3 is notation-wise. So take a look at my screen. And 23.3 is what in notation? So 23.3 is on the right side of the mu equals 23.3. So notation-wise, well, it's the second thing, correct. But what does that mean it is? 23, you would write like if you just said like something is 23.3, like what is it in notation? Like 23.3 is what value? It's mu naught. It's mu naught. It's not our average, it's the hypothesized average. Does that make sense? So it's the hypothesized average, it's mu naught. The independence condition is probably satisfied, can be reasonably assumed. Nearly normal can reasonably be assumed. We shouldn't do that. Come on, my Pearson, because what sample size we got? 40 men? Not that large. Doesn't say the population is normal. Not that large of a sample. Therefore, using the student T model should be reliable. I don't like that. That is some not good statistics right there. That is some shoddy statistics. Okay. I didn't like those answers. I was like, 40? You should look at the data. Could be heavily skewed for all you know. It could be heavily skewed. I want to see the data first. Make data-driven decisions. So we've got right here the notation, so I'll just kind of tell you what it is. They're giving us, did not get it right. Oh, they're just asking. Mu naught is equal to this. Oh, and then they want this. Okay, so how do we get the degrees of freedom? I think this is going to be the right one, yeah. Really want us to write this in right here? I wonder if, let's see how good my Pearson is. N-1, great job. So there's 39 degrees of freedom. And mu naught is equal to 23.3. Wonder if, can't get mad at me. Nope, got mad. That's fine. Pretty sure it wants the notation here. Oh, wait. Let's see if it'll let me. It wants me to put in the value. I wonder if I can do this, though. 40. And then, can I not put in the exponent? I'm being like mean to my Pearson. There we go. Will it accept that? Okay, it really doesn't want to accept that. Square root of 40. S over square root of n. Okay, that should be right. I've used up all my attempts now. So this is where the sample size is. S over square root of n is the standard error. The t statistic is found via y bar minus mu naught, the sample mean minus the hypothesized mean over the standard error. The hypothesized mean is 23.3. The standard error is the formula S over square root of n. They'll give us S eventually here. And the degrees of freedom are n-1. 40 was the sample size. And there we go. We should be right. Correct now, unless I've... Okay. I was just seeing if my Pearson would accept weird answers that are technically correct. The mean was this. The standard deviation was this. So it is telling you the sample mean, 40, 24.3, and the standard deviation of 5.2. The t statistic is 1. They already told us the t statistic? Oh my, they're not even making us find the t right here. What is the p-value? I think 1.28. It has to be more than 10%. A good bit more than 10. This is a very hard one to guess. If we get this, we should be very happy. This is a very hard one to guess. It's not that bad. We get 2 guesses at it. No, it's... There we go. 1 guess, done. Let's show how to get it, though. Let's show how to get the answer correct, though. So whenever you're using the t distribution, you have to use the t-applet. Or you have to memorize it all. I don't know. I've done this a lot of times. So you go over here to the t-applet, and on the t-applet, the first thing you put it on a t is its what's. Whenever you're finding t stuff, you have to know this for the t, first things first. What do you put in for the t, first things first? Put this in for the t, every time. You have to know it's what's. Because which t are you using is the question, right? So how do you know which t you're using? How do you know what t you're using? Have to know that t is what's. Anytime you use the t, you have to know its degrees of freedom. Now, when the degrees of freedom are higher, the t is a lot like the z. So that's why I was able to guess it right there, because I know a lot of z-scores. Since I know a lot of z-scores, the t becomes the z. Like if I ask you, what is the t-score for 1,000 degrees of freedom for a 95% confidence interval? 68, 95, 99.7. 1,000 degrees of freedom, 95% confidence interval. What is the t-score with 1,000 degrees of freedom, 95% confidence interval? But if 1,000 degrees of freedom, it's basically the z. So with 1,000 degrees of freedom, 95% confidence interval, 1,000 degrees of freedom, which is how much it's like the z. More degrees of freedom, more like the z. So 1,000 degrees of freedom. What? William, good guess. William, excellent guess. William, I think it's actually basically the exact same. I'm throwing William 50,000 points for taking a guess, and that would be an acceptable guess. If you just used that, you'd probably be close enough. Like you could run your statistics with that, and the differences would be so minute, it wouldn't really matter.
It doesn't matter.
So here's the answer. It's going to be basically, here we'll go to between, it's going to be 1.96. Wait, 1,000, there it is, 1.96, because that's the z-score. Now it's not quite 1.96. If you add more decimals, you can see it's not quite. And as you increase right here, you can see it approaches 1.96. Does that make sense? As you get more and more, I'm going down, it's going away from it now. As you get more and more degrees of freedom, the t will approach the z-score, which the z-score here is 1.96 or 1.95996. So it'll get to 1.96 eventually. But it takes tons and tons of degrees of freedom. But eventually the differences don't matter. It really matters when the degrees of freedom are small, and you can see 1 degree of freedom, the t and the z are very different for 95% confidence intervals. And then as you increase the degrees of freedom, it quickly gets to it. And I think it's at, is it 60 degrees of freedom? It's basically 2. So understanding what you're doing right here is very important. So how did I get this? I knew 39 degrees of freedom, and we are doing a greater than test. So we need to go above, and we need to go to find a p-value, and the z-score was 1.12 or something like that. What was it? It was 1.2. 1.216. And there it is right there. I was off. It was 0.116. It's the area to the right of the t-score of 0.1216. And the p-value is 0.116 rounded, but close enough that it gave it to me with that guess right there of 0.115. So yeah, that's how you can do it. You can solve them out. If you know z-scores, you can usually guess the t reasonably. So what does this mean? This is a likely or unlikely result. Well, this is going to be a likely result, and the p-value is the probability of seeing what we saw in our sample, the age. So getting a sample mean greater than, of getting a sample mean of 24.3, that's not the sample mean. Yeah, that's the sample mean right there. Likely, exactly. The probability of getting a sample mean of 24.3 or older from natural sampling variation, given that the null is true. Do you remember at the very start of today's office hours, we were writing this down right here. If you look at this right here, this is almost virtually identical. The things I try to do with our examples, the probability of getting our results or results from our stream, so a sample mean of this or older, given that the null is true. So this is exactly what we were writing earlier as practice. What is our conclusion? This is a likely result. So in the p-value, going back to the p-value question, where you find the z-score. So this one right here is not a z-score, this is a t-score. This one's a t because it's the mean, and Mr. T is mean. Does that make sense, Abigail? This one's a t-score, and the t-score is right here behind me probably. Yep, it is behind me. There's the t-score. 1.216 is the t-score. You would have to find it from this equation otherwise. They actually solved it for you. So if you wanted, you could plug in the values yourself. You could find the standard error here, which is going to be 40 square root. I'm just solving this formula right here next to this for the t. So 40 square root, and then take 5.2 divided by that. That's the standard error. 24.3 divided by 20. Oh my gosh, no. 24.3 minus 23.3 divided by the standard error, and there it is right there. Is that, yeah, no worries, no worries. The t-score, yep, is found right here. And then see if you can solve it yourself. I just solved the t by plugging in y bar, which is 24.3, mu naught, which is 23. Good to see, Michael, 23.3, and standard error, which is found by s over square root of n, s being 5.2. Plugged into the applet? Yeah. To plug it into the applet, you have to take the t, and so you find your t statistic, which this problem gave to us, which the t statistic is right down here. I don't know why it's showing so much on the screen. The t statistic is down there on the bottom. Go to it. Here's the t. And then you have to go to the applet and first enter in your degrees of freedom. And then are you shading to the right or the left or outside? This is for the greater than, this is for the less than, this is for the does not equals. And then you pick find p-value using t. Does that make sense, Samantha, right there? Find p-value using t. Find p-value using t. And so then you can find the p-value. Yep. Good work right there. So enter in your degrees of freedom, pick the sign of the alternative, find p-value using t, and then enter in the t-score right there where it says x right there. And that'll give you it right there. And we fail to reject the null. We do not reject the null. There is not evidence for the alternative. That means we do not have evidence that it is, we don't have evidence to conclude it's greater than, right? We did a greater than test. Happy the fool. That's got it. That's the full homework. It's a challenging homework towards the end. So really it's just the last few right there. But I like these questions. Can we speed run this question? Speed run. And I hate this can reasonably be thought to be true. It's not that large of a sample. Not that large of a sample. Then we go right here. What's the sample size? 40. Probably still 40. And 40, square root of 40, and degrees of freedom 39 is n minus 1 for the one sample t. Wait, what'd I do? Oh, mu naught. Mu naught is 23.3, the hypothesized mean. And the t statistic was 0.0. Oh, no, that's super close to the, I know what that's going to be. So that's a little bit more than 16%, a little bit more than 16. Nope. Yeah, maybe a little bit more. Nope. Yeah, I guess it is going to be. Oh, it was between our two guesses. Well, darn. Well, we got close. Was it plus or minus point? Whoa. We were within. Oh, great job, Samantha, right there. Let me throw you some 50,000 points, Samantha. Samantha's like, psh, I got that. Here's your p-value, Brian. Yeah, and think about why I was thinking about 16%. So Samantha, why was I? Do you see why I was thinking about 16%? Because the t is basically 1, and 68 is 32 outside. And since we're basically at a z-score of 1, on one side would be about 16%, but we're a little bit more than it because we're a little bit before. Does that make sense, Samantha, what I'm thinking through? If you can kind of see how I'm guessing these, then you understand what you're plotting, because it's like, okay, we're at a t-score of 1-ish. So if you went outside of 68, 32, and 16 above it, then it's a little bit more than that because you're not quite at 1 and the t has heavier tails. So if you understand how to do this, that's even better. So with that, we're going to end here. Great job. Great practice, everyone. Until then, bye for now, everyone. Bye.
Morty, we've got to turn the project in early.